So there's two limit definitions of the derivative, which I almost guarantee there will be a question, I feel like, about this. So for the general use where you're not specified a case, that's the f of x plus h minus f of x all over h as h goes to 0. But then if you are given a specific point, that's where you can use the limit as x goes to a, and that'll just simplify things, especially if a is 0. That's really helpful. But these are, you guys have probably done these before, so I'm just, as a reminder, if a specific point, use the one to your right. General use, use the one on the left. But then they're more so useful for when there's questions about whether or not a function is differentiable at a specific point. So a derivative is defined if, one, the limit definition of that derivative exists. So if this limit exists, that's the first step. And then the second part is that the function has to be defined at that point. For the most part of functions, these are the two kind of things to show that a function is differentiable. So if a question is asking you whether or not the function is differentiable, one, take the limit definition of the derivative, prove that that exists, and then show that the function is defined at that point. And for it to be defined, you're just evaluating f at a certain value. And just on graphs, there's a few ways for a derivative not to exist. So at kind of a cusp, at a discontinuity, and then also at a vertical tangent line. Those are just a few examples graphically where the derivative wouldn't exist. Are there any questions about that? Okay. So primarily you'll see this with.
Can you give an example of where you actually get a cusp?
On the second midterm of flavor C, there was a question where you had to, it basically gave you the graph of the derivative, and then you had to graph the function, and it ended up being a cusp because to the right of a certain value, it was concave up, but increasing, and then to the left of that, it was concave up, but decreasing. So those two concave ups made a cusp.
Okay.
So it's not, I don't know an exact function, but if they give you like graphs, it can create that cusp-like. So this is kind of what we were talking about. In order for it to be differentiable of a piecewise function, you're kind of doing those one-sided limits. So you'll be the limit definition of the derivative of the left side equals the limit definition of the right side, and then also the function is defined at that point. These are a few common questions, especially in the past midterms. They'll kind of ask you, show that this piecewise function is differentiable at a point 0. So the derivatives must equal each other, and then the function must exist at that point. Then you know that it's differentiable, and the derivatives also have to exist. Okay. Really quickly, the few derivative rules. So there's power rule, product rule, chain rule, quotient rule. I'm sure you guys have seen these before. Just keep in mind with a chain rule, you want to start from the outside in and then work your way in to the middle. Quotient rule, it's essentially like similar to the product rule, just don't forget that it's a negative sign instead of a plus sign, and then you can apply the product rule multiple times. The next thing with derivatives is implicit differentiation. This has kind of been gone through, but just kind of a few tips to keep in mind is when you're doing it, rewrite f of x as y. It'll make things a lot simpler. And then also, rather than using like dy over dx, I suggest just doing y prime, so you don't have to write more, and then it doesn't get super messy when you're having like 5 different y prime terms, and you don't know what is what. And then always remember, after you do that, that y is a function of x. So when you differentiate y, use the chain rule. You're always going to have whatever it is, like y squared. That would be 2y times dy over dx, or times y prime. And then after you implicit differentiate, you'll want to isolate for dy dx through common factoring and rearranging. And then also just watch out, sometimes on a few of the midterm questions, they'll trick you. Rather than saying for we want dy dx, they'll ask you for dx dy. So that implies that x is a function of y, as opposed to y being a function of x. So it's essentially the same thing, but suppose up there it was just, this would equal just 2y, but if that was x, yeah, so just make sure you understand whether or not they're asking you for dy dx or dx dy. So if they're asking you for dx dy, x is a function of y, and it's basically just like they're flipped. Okay? And then the next one is logarithmic differentiation. This is when you have kind of a function to the power of another function, and it's used to simplify this. So essentially, as you can see in that example here, we have a function and it's to the power of another function. So in order to simplify this, we take the ln or the natural logarithm of both sides, and then we implicit differentiate that. So by doing what we kind of did before with ln of y, that would be 1 over y times y prime. And then on the right side, you're able to bring down that exponent in front of the natural logarithm because of exponent laws. Yeah? I'm so glad you asked that. So essentially, when you're like natural log differential, you can imagine it, since it's not multiplied by, it's plus, you can almost isolate the e dx as a separate like function. So you can take the derivative of the first part of the function and then add the derivative of the second part of the function. So you don't actually have to include like e to the x in it. You can just, yeah, you can just like keep it separately. So it can help in your equations. Because if it was 1, it would multiply like the e to the x outside. So those are pretty cool. And then simplify it afterwards. Okay, and then lastly, kind of inverse functions. Just quickly going over, it's basically, rather than having x as an input that returns y, you have y as an input that returns x. So if the f of x equals 7, then the inverse of 7 would equal x. And in order to solve this, all you do is you write f of x as y, you swap that y in x places, and then you rearrange and solve that equation for y. And that's all it is for inverse functions, and you can also differentiate that. Yeah, and then derivative, you can use that to determine the derivative of an inverse function. Hopefully, you've memorized most of these derivatives, except just do the top 3. There's no reason to have to memorize cosecant, secant, or cotangent. You can derive those using chain rule and power rule. So what's the derivative of cos x? Who said sine? Who said sine? Yeah, okay, and then same thing with these ones. Just remember the top 3 basically. So derivative of arc sine is 1 over square root of 1 minus x squared. Arc cos is basically the same thing, but boom, there's a negative sign because the derivative of cosine is negative sign, yeah. And then arc tangent, you just don't have the square root. So just make sure you know those so you don't make a silly mistake on the exam. There's a flashcard set if you're interested in helping to memorize these, so you can take a photo of that if you want. The slides will also be posted afterwards. Okay, now this is actually, I don't know, this helps a lot. So we have a right triangle, and we want to find the derivative of sine of arc cos. We could do that using chain rule, but that's bad. That's not bad. That's the long way. I feel like I don't want to do the long way. So essentially, what we're going to do is we're going to use kind of a little trick that you can like, it's pretty simple, but essentially you want to set this angle as whatever your theta is. So in this case, that would be sine of theta, so sine of arc cos. So we're going to set this as arc cosine of x. Okay? So now that we know that this theta is arc cosine of x, we're able to determine where x would be, right? So can anyone tell me which of these sides would be x? Yeah. The bottom, exactly. Okay, so we know that this is x, but then we also know what the hypotenuse would be now, because it would be 1. Okay, so now we can determine what this is, right? Just using Pythagorean's theorem. So we can say that this side would be 1 squared minus x squared square rooted. Okay? Does that make sense? Yeah. So now, what would sine of theta be? It would just be 1 squared minus x squared over 1, opposite over hypotenuse. So then rather than having to differentiate sine of arc cosine, you can just differentiate this, which is a lot easier, right? So if you ever see kind of sine arc cos, you can simplify it using this trick. And that works. You can put arc sine, arc tangent, whatever you want as a theta. That really helps to simplify any like inverse trig functions. Are there any questions about that? Okay. Does that make sense? Okay. Oh, that's what I did. Okay, so those are just some steps in there in case you forget. You can look over and that's exactly what we did. So we did it right. Good job, guys.